So we're going to pick up where we left off yesterday, really. Now, what do I mean by picking up where we left off? Well, we covered factorial a little bit, and we started talking about permutations. And I want to just revisit factorial because it's going to be a foundational idea, right? Just as we've been talking, set theory as a foundational idea, and within set theory we've got this idea of the probability of A being the cardinality of A over the cardinality of the sample space that contains A. So this is one of our building blocks. The other building block is going to be counting. Not that we have to clearly distinguish these two from each other, but we're going to take two different angles. I think I've been saying that. And counting, we're going to start with counting, which we've been doing some of. And then we're going to reduce to factorial. We're going to take that to permutation, which I'm going to call perms. And we're going to take that to combinations, which I'm going to call comms. Okay? So this is going to hopefully give us a solid sense of probability. These building blocks we're going to use to support probability. And the most important concept in probability, I think we've already been talking about. It's this cardinality of a subset divided by the containing set or the sample space. So let's revisit factorial. Factorial is very straightforward, right? We know how to do factorial. 5 factorial is just 5 times 4 times 3 times 2 times 1, which is 120. So I think that idea makes sense. Now, we want to root this into something more concrete, right? We want to think about this in terms of let's use the example from the notes, and let's say we have an urn, and within this urn we have, let's say, how many should we do? Let's do 3 numbered balls. Okay, so we've got ball 1, ball 2, and ball 3. And if we think about it like, if we draw with replacement, if we pull a ball out and put it back in and then draw again, and we do that 3 times. So let's think first about counting, and we'll reduce that to factorial. So let's think first about counting. We can say, let's list all the possibilities here, right? We can draw ball 1, then ball 1, then ball 1, 1, 1, then 2, 1, 1, then 3. Okay, right? That's one round of this. We can draw 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 3, 1. Sorry, one sec. Okay, good. 1, 3, 1, 1, 3, 2, 1, 3, 3, 2, 1, 1, 2, 1, 2, 2, 1, 3, 2, 2, 1, 2, 2, 2, 2, 2, 3, right? And we can keep going with this. Now, how many of these are there? Well, there's 3 objects, right? There's 3 possible objects here, and we're doing this 3 times. So this is 3 times 3 is 9 times 3 is 27. So we should have a total of 27 of these when we're done. Okay, so 2, 2, 3. Then we've got 2, 3, 1, 2, 3, 2, 2, 3, 3, 3, 1, 1, 3, 1, 2, 3, 1, 3, 3, 2, 1, 3, 2, 2, gonna run out of space, 3, 2, 3, 3, 3, 1, 3, 3, 2, 3, 3, 3. So we can start with counting and we can reduce to factorial. Now, we know what factorial of this is going to be. It's going to be 3 times 2 is 6. So if we go through this and eliminate all the anything that has duplicates in it, well, that's going to give us factorial. Okay, so that has duplicates, that has duplicates, that has duplicates, that has duplicates, that has duplicates. This one does not. 1, 2, 3 is a possible permutation. Okay. If we choose without replacement, if we take a ball out and we don't put it back and we choose another one. Then 1, 3, 1 is not. 1, 3, 2, well, that one works. 1, 3, 3, 2, 1, 1, 2, 1, 2, 2, 1, 3 works. 2, 2, 1, 2, 2, 2, 2, 2, 3, 2, 3, 1 works. Notice we have kind of like this a little bit of an emerging pattern here, and I think that's one nice thing about the lecture today, is that there will be emergent patterns that are kind of cool. 2, 3, 2, 2, 3, 3, 3, 1, 1, 3, 1, 2 is a good one. 3, 1, 3 is not. 3, 2, 1 is good. 3, 2, 2 is not. 3, 2, 3, 3, 3, 1, 3, 3, 2, 3, 3, 3. Okay, well, notice that there are 6 of these, and we've figured out all of the permutations. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. So, is there rhyme and reason to this? Well, I think we can say there is. There's a procedure we can take in order to reduce out all the possible ways, all the possible arrangements or permutations of these 3 balls. That's something we can do here. Another way we can think about this is, we have our first selection, and maybe I'll erase this counting as well. I just want to show you that this does root into counting if we really take it that far. So we can think about this as step 1, or selection 1, selection 2, selection 3. And if we select ball 1 first, well, we can only select ball 2 or ball 3 next. And then ultimately on the third one we will do that. So notice we get something like this. Okay. If we select ball 2 first, then we can get ball 1 or ball 3. And similarly, we select 3, we're going to get either 1 or 2, and then 2 or 1. So however we want to approach this, either it's through in any case it's a reductive approach, right? We select one thing, we can't select that thing again. We're going to move on from that point. So that should give an idea about arrangement. And with that idea, we can start answering some questions, okay? But before we answer that question, I'm going to have you code a factorial function. Factorial is one of those functions that it's one of the first functions you learn to code. You're going to code factorial of some number, and let's do 3 minutes on this. So I'll set a timer for 3 minutes, and yeah, go ahead and code the factorial function. Okay, I'm going to go ahead and code through this. So we're going to accumulate against the product of all numbers between 1 and some number, right? So I can say for n in range, we can start at 1. We can also start at 2. Either way is going to be fine. And we'll go up to num plus 1. And we'll say product times gets n, and we can return the product like so. So, with that, I can print the factorial of 5. Let's do 5. And we get 120. So we can see that that's working as we'd expect it to. Okay. So this factorial, what a way that we can think about it is it provides cardinality of the sample space of arrangements or selection without replacement. Does that make sense? So it's kind of the sample space of the arrangements of n or num items. In this case, 3 items. We can see that it would be 6. Or if it was 4 items, it would be 4 times 3 is 12, times 2 is 24. Or 5 items, 5 times 4 is 20, times 3 is 60, times 2 is 120. We can start thinking about this as, well, we've got this number of items. How many different ways can we shuffle it, right? And we can ask the kind of question like, well, how many different ways could we shuffle a 52 card deck of cards, right? And, well, let's just see what this gets us. This is a huge number. This is a massive number. And in fact, it's such a big number that something is happening here on the end. We're actually not able to effectively store the precision out here on the right of the number because the number is too big. This is something that can come up as an issue. We're going to see this come up with, throughout this lecture, where the best our computer is going to do is something like an estimate here. We would need a special data type to be able to hold a number that would be precise out here on the right if there's this many digits of that number. We don't have that. We don't have that data type on hand. The int data type is not going to do it. And that's okay. If we're trying to answer the question, how many different ways can you shuffle a deck of cards? Well, a lot. There's a lot, and an infeasible number of ways that we could have everybody on Earth shuffling cards for their lifetimes, and we wouldn't come close to this. And that's that's kind of cool. So factorial of 52 is a little bit out of the range of what we're thinking about doing. Although we could start thinking about something like factorial of 24, maybe I should print that. That number is a little bit more tenable. It's still huge, right? It's still huge. And I think that's important to notice. It's important to notice. Let's think about factorial of 12. This is going to be huge. All of these numbers are going to be huge. And I think that's really important to see. Okay. So when let's look at this question just to, like if we're going to make this idea concrete, we're going to think about the use of factorial, then let's consider this. And, we can answer this pretty easily. There are 10 people standing in a line for beignets at this restaurant in New Orleans. How many different ways can those 10 people be arranged? Well, factorial of 10, right? That's how many ways we can arrange them. We're assuming they all have different names, or names that start with different letters, let's say. Given that the line was formed organically, right, people just get into line, what is the probability that they're standing in that line in alphabetical order? Okay, well, I don't know if this is immediately obvious, but we know how to answer that question already. There are 10 factorial different ways that they could be in line. There's only one way that they could be in line in alphabetical order. And so this is just 1 over 10 factorial. That's all that is. That's the answer to that question. And if you think about it, if you start seeing these probability questions as like, oh, it's sort of like just a logic puzzle, right? You're just sort of like figuring out, like the math itself is not hard. It's more, what are they asking, Well, the trick here is to understand that there's only one way to have them be in line in alphabetical order. And so 1 over 10 factorial is the probability that they will end up in line in alphabetical order. And I probably don't have to tell you this, but that's going to be a tiny number, right? That's going to be 1 over, you know what? Shoot, I should just run it in the, I should run it over here. So I'll do 1 over factorial of 10. That is a tiny number, right? And the way, if you're not familiar with this notation, the way that we would read this is, okay, well, we're going to move this decimal place 7 to the left. So 1, 2, 3, 4, 5, 6, 7, right? That. That's a tiny probability. And I hope that kind of contextualizes probability in a sense. Now, would we say that them being in line in alphabetical order is an unlikely event? Yeah, sure. But we also live in this strangely deterministic world or universe where unlikely things happen all the time, and once something happens, right, it was a sure thing that it would happen, so probability kind of gets turned on its head in kind of a strange way. That's a little philosophical, but we don't want to assume offhand that just because something unlikely happened that it's magical in some way, right? At least, in some classical idea of being magic. Oh, it's so unlikely that it proves the existence of magic or something like that. No, it's just unlikely things do actually happen, because we live in such an amazing universe. Okay, so factorial is a special case of permutations, and I kind of touched on this last time. So permutation is the way I'm going to describe it is it's an arrangement of let's say k elements out of n elements. Okay, so it's an arrangement of k elements out of n elements. So if we have 10 people, we have A, B, C, D, E, F, G, H, I, J, K, I believe. 1, 2, 3, 4. I should know this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I did the same thing yesterday. Okay. Up to J. If we're trying to think of some arrangement of 3 of these, then we would say N is 10 and K is 3, right? for selecting some three of these, like maybe B, F, and H, and the arrangement being FHB or something like that, that's one arrangement of three of them. The way that we write this in notation is we say n permute k, or n permute r. You know, r is commonly used instead of k. I use k because it makes sense to me in light of a whole bunch of other things, but it doesn't matter which you use. For the sake of not getting confused on it, let's just use k. NPK, the way we would write this is 10 permute 3 of them. Okay? 10 permute 3. So you would imagine that the way that we would do this permutation would be very related to factorial, right? Like it's going to be directly related to factorial, and we're going to think of it in light of factorial, which is pretty easy to do. So if we were doing 10 permute 10, right? If it was 10 permute 10, then we would have 10 factorial. It would just be 10 factorial, right? Now, since it's 10 permute 3, we're going to reduce the space. We're going to reduce the space by 7 of those 10. Okay? So this works out to be, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this, of course, is going to be 7 factorial, which is going to be, 7 times 6 times 5 times 4 times 3 times 2 times 1. And notice we can cross all of that out. And 10 permute 3 is just 10 times 9 times 8, right? Or 720. So that's basically our review from yesterday. The formula I'm using there for NPK is going to be n factorial over n minus k factorial. That's our permutations formula. Okay? There's this thing that we say about this. We say order matters. Order matters. Now, what does that mean? Why do we say order matters here? Well, if we're choosing 3 of those items out of 10, and we choose, I don't know, A, B, and F, or whatever I said, A, B, and F, ABF is a different permutation from BAF, or AFB. Those are 3 different permutations, and we need to be conscious of that. We need to be aware that those are 3 different permutations. So, the order matters here. That's what's apparent. If the order didn't matter, then these would all be the same exact selection. If it didn't matter what order the selection was made in. So let's think about permutations from counting. We kind of already did that. We counted count in a base n system. We did this with base 3, right? With 1, 2, and 3 as the symbols that we were using, or the numbers. Now, the second part of this that we did was you reduce the count. You reduce counts that have duplicates. You reduce. So you reduce the counts that have duplicates, and then you consider k of those items. So if we were thinking about this in terms of, well, I don't know, 10, let's do 5 items, A, B, C, D, E, F. Well, there's one permutation right there. Another permutation would be A, B, C, D, F, E, and then maybe A, B, C, D, A, B, C, F, D, E, and then we can swap those ones as well, F, E, D, and we could keep going. Now, this is 4 permutations out of, 6, I said 5, I meant 6, out of 6 factorial possibilities, right? This is only 4 of those, and of course this is going to go on, 6 factorial minus 4 times, more than this. If we are only considering k of these items, let's say 4 of these items, if our k is 4, then after we construct all of these, we can get rid of these 2 leftmost items, and we're going to have all of the length 4 permutations out of our length 6 permutations, right? So factorial gets us everything. Permutations gets us the, some reduced number of items from factorial. So that's our next reduction here in step 3. So I'm going to have you code a permutations function. This is not going to be to generate permutations, okay? I'm going to walk us through generating permutations. This is just going to be that permutations formula that I wrote out earlier, okay? So we can call this permutations. I'll put it up here in the right. Def permutations, and you're going to put in n and k, right? Those are going to be your 2 parameters. So we'll do n and k. That's going to be our stub here. And let's do, how many minutes should we do on this? Let's do 4 minutes. Yeah, let's do 4 minutes on this. Okay. Go ahead and code the permutations function. It's going to rely on factorial, and that probably means I should paste in. Oh, I did paste in factorial. Okay, good. So permutations, of course, is going to rely on factorial. We can see it up here. Go ahead and code this out. All right, so I'm going to show you two ways to write this, and they are procedurally different. One is a little bit better than the other one. However, either one is completely legitimate. Okay, so we can just directly translate this function, this NPK, right? We can just say, well, this is factorial of n divided by factorial of n minus k. That's really it, right? You just have to return that. If we can test this with, why don't we test it with 5, n is 5, and let's permute 5. I'm not actually done with this function. I'm going to add something to it, but notice we get 120.0. Okay, well, we're counting, right? So we don't actually want this to return 120.0. Not that that's a problem, but I'm going to go ahead and cast it to an integer anyway. I think it makes a lot more sense for that to be an int. Okay, so that's one version of permutations that we can use. I'm going to try to rethink permutations because we're going to run into. Remember when we were running factorial, like on huge numbers? Factorial of 15 or 24 or any of those big numbers, we're going to start losing. We're going to start losing precision pretty quickly, and we can make a slightly better function. Not that you have to think about this in this way, but let's make a slightly better function. So I'm going to define a second version of permutations, and it's going to look a lot like factorial. So except perm here is going to be was prob or product actually in the earlier one. So I'm going to call this perm, and I'm going to say for I in range n to n minus k, going in reverse. Okay. So if we think about this, we can notice that, for example, if we were doing 10 permute 3, we would start at 10 and we would go down to 7. Okay. We would not include 7, so we'd do 10 times 9 times 8 because we're traveling in reverse. So we're going to perform less operations, in some sense, less operations than the factorial function would. And we're going to be able to handle much larger calculations this way. We don't really need to worry about that too much, honestly, for what we're doing, but I just want to show you. Oh. What? Oh, interesting. That didn't even occur to me. This is not always going to work, right? Because it's not going to go from. Oh wait, no, this should work. Ah, that's the issue. Oh, my bad. Okay, here, there we go. So this works, right? We get 120. Now, let's try something. Let's make a comparison between these two. Let's do permutations. Let's do 20 permute, I don't know, 12. And we'll see, let's see how this performs differently for these two different versions of the function. Oh, it doesn't. Okay, let's try some bigger numbers. Let's try 30 permute 17, maybe? And see if that performs differently. We might even need to go a little bigger than that. There we go. So in this one, These are, that's like a 30-something thousand, no, 3 million or 300,000 or so discrepancy between the two. And my bet is that even though this one doesn't look it, the second one should be better than the first one, because we can handle larger values. So just wanted to throw that out there. There are better ways to perform the same operations. Okay, so let's look at a story problem here and just consider how to answer it. So we have 10 students, and we're conducting a science fair. There's a first, second, third, and fourth prize. How many different arrangements of those 4 winners is possible? Well, this is simply, we've got 10 students, so n is 10, right? N is 10. We're considering 4 of those students, k is 4. This is just permutations of 10 permute 4. So it's kind of that easy to consider this. We could do it by hand as well, but notice we're getting this answer 5,040. So 10 permute 4 is 5,040. There's 5,040 different ways out of 10 students for 4 of them to win first, second, third, and fourth prize. And I think that may seem like a lot more than you would expect intuitively. And part of looking at this stuff is to rebuild your intuition. Because humans, you would think we would be much better at probability than we are. It turns out we're not that great at it by default. But we can build a lot of intuition around it, and that's one of the goals of what we're doing here. Okay, so let's build out permutations intuitively, and I'm going to build a base 5 system. So base 5, and this is going to be I'm going to build it out of some symbols. So let's do some sports, I guess. Tennis, swimming, I don't know, racquetball, racquetball. I don't know. That might not be how you spell it. It doesn't matter. Tennis, swimming, racquetball. Shows how into sports I am. Basketball and soccer. Okay. All right. So we've got these five objects. And what we can do is we can first count. We can do sports counting. And sports counting, I'm just going to collect into this our counting, right? So for sport 1 in base 5, this is base 5 again because there are 5 objects in there, 5 different symbols that we can consider. And we're going to consider how many different ways that we can arrange these 5 sports. Like maybe there are 5 big games or something, and a network is trying to arrange them, and they're wondering, well, how many different ways can we arrange these over some slot of time? So I'm just going to say sports counting dot append, and I'm going to append a list that's SP1, SP2, SP3, SP4, and SP5. Okay. So now we can take a look at this. We can see sort of how this counting system works. We've been doing this, but let's just look at it again. Let's do for sport in sports counting. We'll print the sport. And we're counting from, tennis through soccer. Like tennis, 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 through soccer, 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 soccer. So this is what our counting system looks like raw. And, this is 5 to the 5th power, right? There are 5 elements, and there are 5 positions. It's 5 to the 5th power, and we can see that. Okay. So we have that. We can now reduce that space. Okay. So let's do that. Oops. Why don't we reduce that space? I'm going to say sports perms for sports permutations, and I'm going to collect into this. So for SP in sports counting, we're going to assume offhand that it is a permutation, and then I'm going to say for sport in, well, let's do it like this. Let's do sport number, and we'll do sport in sport number, okay? So we're now going to look at each individual list and each element in each individual list, okay? And we're going to say if, how do we want to think about this? If, not sorted, if SP number dot count of that sport is greater than 1. If there are duplicates, right? If there are duplicates, that's what this question is asking. Then we know it's not a permutation, and we can stop analyzing that sports number, okay? And we can say if need an equal sign there. If the permutation, if permutation is true, then let's do sports terms. We can append that sport number. Okay. So we just reduced our space. We just reduced out everything that we don't care about. You know, anything that has duplicates, we just got rid of it. So I can say for sports number in oh gosh, sport perms. These are not great names. Sorry about that, but they are names. So we can print that sport number. Okay. So, oh, getting a whole bunch of nuns in here. Sorry, one moment. Sorry about that. Okay, so I'm getting these nuns. Let me just figure out what's happening there. Oh, I'm printing a print. So why don't I do that? Okay, so now we can see our permutations. Let's analyze this for a second. There is an emergent pattern here, and it's not a pattern that we need to know. It's not a pattern we need to recognize. But we do want to recognize that this process that we're taking has a pattern in it. So I'm just going to annotate this a little bit. So notice soccer moved there. Basketball moved there. And then soccer moved back. And racquetball moved there. And basketball moved all the way over there. Okay? Then soccer moved here. And racquetball moved here. And so on. There's something systematic happening here. There is a swap order that's happening. And it's within our power to analyze that and write a better algorithm. Okay? That is in our power. We're not going to write this algorithm. We're going to write a more well-known algorithm. But I just want to point out that the pattern of swaps is something emergent through this reductive process. And we could, instead of reducing, which takes all these loops and loops and loops and a lot of processing power, we could write something that instead performs swaps and does not take a counting approach at all. And that would actually be more optimal. So that's a bit of a theme of this lecture, is that there are better ways to do things sometimes. And, you know, let's say better algorithms. So the algorithm that we're going to look at is called Heaps Algorithm. And I'm going to open that up on Wikipedia. So there's this page on Heaps Algorithm. And I want to just see if I can get a sense of, oh gosh, hopefully this image will actually load. Maybe I can just zoom in on part of it. So looking at this, notice that there is a swap pattern, and that pattern is going to be fairly repeating as we go through it. Now, I know, scanning this, scrolling through it, we're not going to be able to really get a strong sense of that pattern. But if you sat down with a piece of paper and a pen, you would see that there is indeed a pattern here. And that's really great. Now, not only do we have this visual pattern, we also have some algorithm details here. We've got details in a formal language, which is just an algorithm language, not necessarily a real programming language. We have details about how this procedure would work. There's a couple different versions of this. One is a recursive version. We're not covering recursion in this class. We do have some materials on recursion in the advanced Python section on Learn, way at the bottom. But instead, I'm going to go ahead and code out a non-recursive version of the program. So this is going to, well, how do I say this? This is a bit of a demonstration, and we would not expect you to code heaps in an interview, and maybe not even until toward the end of you being in the DSI. But coding heaps algorithm is the kind of thing that you might expect to do in a job interview, right? Somebody might give you this description of an algorithm for permutations and say, hey, code this. We're going to sit down with you and talk me through coding out this algorithm based on the formal language that it's associated with. So I'm going to, let's see. Since we're considering something that swaps, let's start there, okay? I'm going to code out a type of function that you might be expected to code sooner than later, okay? So this will be in the in this Python file. This will be where Heaps Algorithm starts. I'm just indicating where that is. There is a swap, right? Where we take two elements. This should not say get, this should say def. There's a swap that occurs. And it's a swap of items in a list, okay? And we're going to have two indices. We're going to have the index of one item to be swapped and the index of the other item to be swapped. And we're just going to turn them around, right? So how do we do that? I'm going to do this in a more classic coding style, something that you might see in other languages. You could write something better, something a little bit nicer in Python, but the idea will be essentially the same. So I'm going to make it first, for Python purposes, I'm going to make a copy of the list. That's something if we're going to modify an object, we'll tend to make a copy of it instead of modifying the original object. So I'm going to do that. And I'm going to use a temp variable. So I'm naming this temp. And in temp, I'm going to put index 2, the item at index 2, into temp, okay? Once I've done that, I can say, well, it's okay at that point to write over what was in index 2 with what is in index 1, right? And now I can say index 1 is going to get temp, and I can return the list. Okay, visually, how do we think about that? So I've got some list, and let's say we have A, B, C, and D, and E in it, right? And this is index 0, 1, 2, 3, and 4. If I want to swap indices, let's say 0 and 3, what I'm doing is I'm making a temp variable, right? I've got these 3 boxes. I've got this is a box, and this is a box. Box 0 contains A, box 3 contains D, and I'm going to have a temp box. I'm going to take this, the item in box 3, I'm putting it in temp, and then I'm taking the item in box 0 and putting it in 3, right? And then I'm taking the item in box temp and putting it in box 0, okay? That's all that is. It's just I'm setting something aside and swapping it in. And that's exactly what this function is doing. So, given how we're thinking about heaps, well, this is just going to facilitate our swapping of things in heaps to generate permutations. Now, to be really clear and honest about this next little whirlwind of code I'm going to perform, I'm going to talk through it. I don't expect you to understand it deeply, but I want it to be here for you to be able to pick apart and to understand it. This is also in the slides for today. Okay. Okay. So I'm going to write heaps, and this is a non-recursive algorithm. I'm just indicating that because if you go and you look it up and you read on it, what you'll probably find is a recursive form of this. I tend to default to non-recursive algorithms if I can. Okay, so the first thing I'm going to do is I'm going to make a copy of the list, as we often do. So list.copy. And then I'm going to essentially create an object that holds the state of things. I'm going to call this holds stack state, right? And this is just going to be a little a list of indices, essentially. And it's going to be initialized to 0 values for the length of the list. So that's kind of cool. That's just like a record keeper, okay? And then I'm going to collect our permutations. And in our permutations, I'm going to get the first permutation, right? So here's perms. This is what we're going to return. I'm going to say list copy, and I'm going to get the initial state of this up to the kth position, right? Because remember, we're taking k elements only out of however many elements we're going to permute, right? Remember, it's n permute k, so I'm going to take up to the kth element here. And you'll see that this idea, this form, is going to exist throughout this function, okay? So I'm going to do this. I'm going to set this value I to 0. We'll call this a stack pointer, and it's going to help us point at items in our stack. So now I'm going to use the infamous while loop, which we constantly tell you to avoid, but it makes sense to use a while loop here. I'm going to say while I is less than the length of list copy, okay? So that might tell you something about I. You know, we're not going to increment it by 1 every loop or something like that. We're going to modify it and remodify it and remodify it. And it's going to be the condition that decides when we stop. So I'm going to say if C sub I, right? I is our stack pointer, and we're looking at the position in C. So this might imply that we're starting with the leftmost item. If that is less than I, okay? So that's kind of an interesting little dilemma. How do we pick that apart? On the first pass of this, it'll be I will be 0. And if C sub 0 is less than 0, well, what is C sub 0 on the first pass? It's 0, so obviously this condition will not run on our first pass of the loop. And we can say if I mod 2 is 0, in that condition, we're going to perform a swap. So list copy is going to get a swap of list copy with the 0 and ith element in the list. Okay, so you're likely a little bit lost, but that's okay. I just want to show you that we have conditions that we can pick apart. We can pick apart this logic, and we can finally, at the end of this, get a very kind of optimal algorithm to do something pretty cool. And I'm going to code 2 of these out, one for permutations and one for combinations, which we're going to talk about shortly. Okay, so in the event that we can't mod 2, if we can't mod I by 2, and have no remainder, then we can swap list copy the value in C sub I with the value of I. So we're kind of moving our position of interest to the right, depending on these conditions. And I think there's something kind of amazing and simple about this algorithm in that sense. Okay, so so we've got those two conditions, and then we can ask, well, if this value, if this permutation, list copy up until the kth position, is not already in our collection of permutations, then we can append it. We can say perms.append list copy up to k, right? So an implication that you might see here, if we have to check for membership, it means that we are going to get some duplicate permutations here and there. And if we get a duplicate permutation, we don't want to add it to our permutations. That just makes sense. And also what that might indicate to you is that there's a little bit of unnecessary computation that happens here, because this algorithm is not perfect. It's not. And that's okay. It's going to get the job done. And I believe, I might be wrong about this, but I think this is the essentially the most optimal algorithm. There are a couple other algorithms that have similar run time measures, right? We call time complexity is what we call that. But I think Heaps is essentially as good as anything else. Okay. All right. So I increment the counter for that position C sub I, and I also reset I under these conditions. Now, if that's not what I do, if C sub I is not less than I, then I'm going to do something different, and I'm going to say C sub I gets 0. So I actually reset that counter position, and I increment I by 1. Okay. So notice on the first pass of this algorithm, we're actually going to commit this else statement, not the if statement up here. Okay. So that's it. Actually, we have at this point collected our permutations. All right. So let's run this on our base 5 and just see if it works. It's always important. So we've got base 5 down here. We should be able to get all our base 5 perms. So I'll call this base 5 perms is going to get this, and we'll pass in base 5, and we'll set k to 5 to start. And let's see what we get for perm in base 5 perms. Let's print that permutation. And we'll probably find that there's an error or not. actually. We found that there is no error. That's great. Okay, so there is something systematic happening here, and that's really important to see. So notice the first thing we're swapping here, tennis, swimming, gets swapped swimming and tennis, everything else stays the same. And then we pass racquetball over here, racquetball, tennis, swimming, swimming, tennis, racquetball, swimming. This is systematic. And if you think about it, we've actually taken what we were looking at before and flipped it. I believe this is a clear flip of the reductive algorithm, or the results of the reductive algorithm that we saw before. I'd have to pick it apart to make sure, but I'm pretty sure. So that's kind of amazing. They're doing the same thing. One's doing it way better. And also what we can do now, fairly easily, hopefully we can do this, should probably test it. We can see if this works for permuting 3, so 5 permute 3. And it looks like it does, which is pretty great. So these are all the 3-sport permutations. Maybe there's only time slots for 3 sports, and they're all the same length. And we want to look at every possible arrangement of that for 3 out of the 5 available. Okay. So I know that probably has some of your brains on fire a little bit. Let's take a 5-minute break, and when we come back, we'll look at combinations, which is kind of the further reduction from permutations, and we'll go through a problem related to that. Okay, I'll see y'all back here in 5 minutes. Okay, so we just talked factorial, permutations. We're going to take this a little bit further in the reductive sense. We're going to think about combinations, okay? People will often get combinations and permutations mixed up, and it makes sense that people do that because, well, think about a combination lock, right? The order matters, right? The order matters. The numbers that you put in, like 12, 30, 15, or something like that, is a different combination from 30, 12, 15. And really, this should be called a permutation lock. It's not a combination lock. It's a permutation lock. Combinations as a concept is fairly different. And I think with these, it's really important to... Oh, am I not sharing my screen? Oh, I'm not. That's strange. Are you all able to see my screen now? Okay, cool. Yeah, that's really weird. It showed that I was sharing it, but apparently it wasn't. Okay, cool. All right. So yeah, let me kind of restate that. Combinations gets confused with permutations because of the way that we use the word combination just in everyday English. It's something that implies some kind of order, but it doesn't actually, in a mathematical sense, imply order. You want to tie these things to some kind of real-world example. Okay, so combinations versus permutations. If you have to distinguish those two things, I think one of the best ways to remember combinations is that, well, how many is through this question. How many 5-card combinations are there? Like poker combinations from a deck of cards, from a 52-card deck. Does it matter? Does it matter the order in your poker hand? No, it doesn't. It doesn't make a difference how you lay your cards down, right? If we just think about this as, well, they could be in any order, right? Doesn't matter what order they're in. This is an ace of spades and, whatever these other cards are. It doesn't matter what order those are in, what order you lay those down. So if you can tie this idea, 5-card combinations from a 52-card deck to the idea of combinations, I think that will help make that differentiation. What can we think of for permutations? I think permutations is easiest to remember as you have 10 students. How about this? 10 students. And they're in a science fair, right? This is kind of the question we saw earlier. There's a first, second, and a third place. How many ways can you permute 10 students across the first, second, and third place? These are just archetypal ways of thinking about this. And you'll find that with not only with these kinds of problems, but also with the discrete distributions, it's really good to tie into some real-world example, something that you can say, oh, here's an example of something that follows a binomial distribution. It's a binomial distribution question. And if you can think about it that way, you can think about other phenomena that look like that. So, combinations can apply to a whole bunch of different phenomena. So 5-card combinations from a 52-card deck. Well, let's say you play Magic the Gathering. How many 7-card combinations can you have from a 180 card deck, right? It's the same question, but you've slightly changed it, right? Or you're building a basketball team and you've got a squad of 21 players. How many 5-player combinations can you have on the court, right? It's the same question. It's the same question. And that, I think, tying this into some archetypal form is going to help. And then you can extrapolate from the archetypal form. Okay, so we're considering combinations. So remember, permutations had this formula, n permute k, where we said this is n factorial over n minus k factorial. And if you think about it, you could have a number of permutations of something that contain all the same elements. And if you have all those permutations, that would actually only be one combination. So we have A, B, C, C, A, B, B, C, A, and so on. These are all different permutations, but they're all one combination, right? Those are all a single combination. And if you think about that, then what we need to do for permutations, to turn it from permutations into combinations, well, we need to reduce the space. And we actually do that very simply by just putting a second k factorial in the denominator. It's pretty much how that happens. And if you think about why that is, right? If k factorial represents all the arrangements of k, well, this isn't all the arrangements of k. I could put A, C, B in here and so on. But imagine, there's more of these. We reduce every different permutation of these 3 items into one combination with that little piece of math right there. We just divide by k factorial. That's what that's doing. So n factorial over n minus k factorial multiplied by k factorial. That is a fairly easy function to write in Python. And yeah, I'm just going to have you code that out. Let's take 3 minutes on it. Have you code out the combinations function. So I've got the formula here. It's really just translating this directly into Python. That said, if you want to adapt the more optimal permutations function, you're welcome to do that. I hope I actually put that in. Did I put that solution in before? I did not. You know what? Sorry about that. Let me grab our permutations function from above. So we've got these 2 permutations functions. These will probably help if you're confused about coding combinations. And I'm not sharing all the code from today, mainly because it's in the repo and it's just kind of there's going to be a few different walls of code, so I'm just going to share specific snippets of it. Okay. All right. 3 minutes. Go ahead and code the combinations function. Okay, so I'm going to code this in two ways, sort of like what I did with permutations. And the first way is just a direct translation of that formula that we're seeing there. Oops. So this is n choose k, right? And this is going to return factorial of n divided by n minus k, right? Which we're going to take the factorial of that. And we're multiplying that by the factorial of k. And you want to be, just judicious with your parentheses in this. I think, there's a chance of messing it up a little bit if you don't do that. Okay, so that should work. I also want to make a slightly more optimal version of this, and I'm going to give it the same name. I'm not saying that that's a good practice or anything like that. That's what I'm going to do. And this is going to be essentially a copy of the more optimal permutations function from above. And I'm just going to say for I in range, n to n minus k, going in reverse order. And, permutations times gets not 1, but times gets I. And we return the permutation divided by factorial of k. So mathematically, that's exactly the same thing. What I didn't do up here is I didn't cast these to integers, but I want to do that, again, because it doesn't make sense for them to not be integers. We're counting, right? We're counting, and it only makes sense for those to end up being integers. Okay, so I'm going to go ahead and I'll copy these in. I should probably see if they work first. How about we do combinations? Let's say we have a basketball team of 21 people, and we're trying to think of all the 5-team combinations that are possible. This will answer that question. And I hope there's some sense of the utility of this, right? If you're ever thinking about, well, how many different basketball teams are possible out of these 21 players? This is the answer to that. This is actually the answer to that question. It doesn't mean that any one of those is going to be the best version of that team, but there are a lot of different ways you can put 5 players from a 21-person squad on a basketball court. And that may be shocking, right? That may be a little shocking to your sensibilities. There's over 20,000 different ways that they could be on the court together. So, maybe an implication there is that you can't just use brute force if you're a basketball coach to pick what your best team is going to be. You have to use intuition and analysis and do these things. Otherwise, what are you going to do? Try every 5-person squad, that's possible? Like how are you going to go about doing that? There are a lot of options, but you're probably not going to brute force and just try every combination. Okay, so similar to what we did with permutations, I'm going to try to build out some intuition here through the reductive approach, and then I'm going to code a better combinations algorithm, actually based on the tool for combinations that's in itertools, which is something you can import to do combinations. And by the way, maybe I never mentioned this, but you're probably not going to code combinations from scratch in the real world. You're going to call out to itertools, and you're going to get combinations. It just makes sense to do that. Okay. So this is what I'm going to call an expensive counting approach, and let's use that same idea of a basketball team, but instead of 21 players, let's think of 11 players. Let's say we have an 11-person squad. We're trying to choose, trying to figure out, get a list of all the combinations of 5 of those players. So the number, we know what this answer can be. We've got a combinations function, and we can do 11 choose 5. We can do that. We can figure out how many there are. So if we want to actually construct these combinations, we might have to do this a little bit different. We can construct a counting system where we've got 11 symbols, and we'll build this from range 1 to 11. Let's assume there's no player with the 0 on his number or on their number. We have players 1 through 11. Okay. So we can consider every arrangement of 5. Every arrangement of 5. So this is going to be counting. This isn't actually arrangements yet. Let's do every number in base 5. Let's call it that. So possible 5, that'll be an empty list. And then we're going to do this nested for loop thing that we've been doing. Again, this isn't the only way to do this, but it is a way to do this that is not confusing, hopefully. So I, J, K, L, and M. And then we can say possible 5 dot append, and we are going to append I, J, K, L, M. Okay. So now we've got every possible 5. But these aren't arrangements, right? This is counting. So let's build our permutations from this. Let's reduce out to permutations. And for permutations, I'm going to do something a little bit different. Remember the list set trick that we talked about? I'm going to use that. So for each 5 in our possible 5, if the length of list of set of 5 is 5. Remember, the list set trick right here, list of set of 5, is going to leave us with some items that are shorter than 5, right? A lot of them, actually. Like 1, 1, 1, 1, 1 is going to reduce to length 1, actually. So we have to have all unique elements for this condition to result in true. So it's just a nice, easy way that we can do this. And then if that's true, well, we know we have a permutation. We can just append that permutation to our permutations. So now we have our permutations. Now we can reduce out to our combinations. Okay? So I'll say for each 5 in permutations, we can create a sorted version of that 5. Okay? This is going to give us a canonical form of this, right? If we have A, B, C, and A, C, B, and B, A, C, if we sort them, they're all going to be A, B, C. So we don't want to collect duplicates in this. So this is sort of like a deduping mechanism. And we can say if that sorted 5 is not in the combinations, in that case, we'll append it, right? Combinations.append the sorted 5. And we can return the combinations. Okay. So we should have a working function now. And I'll say for roster in, actually, is roster even the right word? For team combination, how about that? In basketball combinations, I'm just going to call the function directly, and we can print all of these. We can print these team combinations. All right. And remember, these are going to be player numbers. These are all the team combinations. And we can find out how many there are. It doesn't look like there's that many, actually, but let's just see. Let's print the length of the team combinations. And let's also let's also snag this number of combinations up here, right? Just to make sure that these match. I suppose there's a chance that they don't match if my algorithm's a little off, but I think they should match. Let's find out. $5 and $4.62. Okay. That does not seem... Oh, okay. I see what's going on here. I need to separate this out. Okay. This is going to be... I'll just call it comms. Why not? B comms. Okay. Let's try that again. All right. So now that I'm actually looking at the right thing, let's see what we get. 462. So that works. We can see that it works. We can also see we can see an emergent pattern here as well. Now, I'm going to code through a better algorithm, okay? And similar to heaps, this is not something that I would expect you to retain. It is something that I want to show because, oh, you know what? You know what's more important than that? I want to show you a different way to intuit this. And that's through sampling. So let's think about this. Combinations via sampling. Okay. Sorry, I was about to jump into this other algorithm, but if we don't get to that, that's fine. But I do want to get to this because this is very relevant to the kinds of things that we're going to be doing in the next lectures on discrete distributions. So I'm going to import choice here. Oh, you know what? I think I may have... No, I didn't. Okay. So I'm going to put that at the top. That just makes sense from random import choice. And remember, choice just chooses out of a list of stuff. So what I'm going to do here is I'm going to sample instead of count. And we're going to get to the same answer, but we're not going to get to it in the same way. We're going to get a list of combinations, but we're not going to be able to see the pattern from counting that gets us there. However, this algorithm is going to be somewhat better. It's going to be somewhat less expensive, especially for certain, for larger team sizes and things like that. So I'll call this basketball comms sampling, and we'll set our team size to 11. And notice, because I'm not taking that fixed counting approach, I can vary these, right? I can vary the team size and I can vary the number of players, and that is a nice aspect of this. That's a nice aspect of a sampling approach. So again, we've got this player range, and we can just go from range from 1 to the team size plus 1, right? So that looks a little different from the last one, but essentially we're doing the same thing. And now I'm going to use the combinations formula from above, okay? So I'm going to say while the length of this collector is less than the combinations of team size and number of players, right? Team size, choose number of players. Then, while that is less, we're going to continue to add players in. So I'm going to say, well, there's this initial player combination. And this is one of those things that, looks awful to me, but it makes sense in this situation where I have a nested while loop. And I'm not an advocate of this, but it makes sense logically in this sense, in this situation. So while the length of each player combination, right, we're sampling a player combination first, is less than the number of players. The number of players by default is 5, right? Then we can say if that player number is not already in the player combination, then we can add it to the player combination, right? Player combination.append, we can add the player number. Okay, so that's how we build a squad. That's how we build a team. And we can modify this to make it more canonical by casting it to sorted, by sorting it, by restructuring it to be in order. Okay, player combination gets sorted player combination. That means that we can now just check to see if that sorted version is in the combinations that we're collecting or not. If it is not in there already, well, what I'm going to do here, because I think this is nice to watch, I'm going to print it, but then, of course, we're going to append this. So combinations.append the player combination. Okay? And when it's all said and done, of course, we return those combinations. Okay, so let's set a team size, same thing we did before, set a team size to 11, and then the number of players we can set to 5. I also want to point out, we don't necessarily need to use a list here. I'm using a list to show that we lose order. We lose the underlying pattern, okay? It would make more sense to just use a set here, right? Because you cannot add duplicates to a set. And we could just look at the length of the set. We could simplify this code somewhat by using sets instead of lists. I'm focusing on lists here because I think where we're at right now, I don't want to introduce another data type and get everyone confused. But this would be better to use. It would be better to use a set here, actually, right? Because a set inherently can't have duplicates. We don't want duplicates. We could use 2 sets, in fact. Okay. So team size is 11, number of players is 5, and we can go ahead and run this. So the first thing, well, since we're going to output everything, I'm just going to print the length of the thing we end up with, okay? The basketball combination sampling, I'll set team size, number of players, and that's it, right? Yeah, number of players and team size. So, and I also want to print, what we get out of our original function, just in terms of how many combinations there actually are. So, with that, let's watch this happen. Oh, player num is not defined. Well, let's fix that first. So that's on line 184. If player num. Oh, I need to build a player num. Yeah, sorry about that. I actually need to get this player number, and it's going to be a choice out of the player range, right? Okay, so let's try that again. Now, that went pretty quick, right? We didn't actually get to watch the construction of this, but it worked. This approach worked. Let's up the number of players. Let's say we have a team size of 21 and see how this goes. Okay. There's a lot more, right? There are a lot more combinations here. And we're going to get to a point where this starts slowing down. And I want to say offhand that if we were trying to do this with a counting approach, it would be somewhat intractable, okay? We would have, it would just take forever. And this approach, the sampling approach, is actually going to get us there a little bit quicker, surprisingly enough. And we're just watching the process of it now. Everything we're seeing here is, combinations that it's finding that are not already in our list of combinations. Now, imagine as we get near to filling out those combinations, near to getting all of them, it's going to take longer and longer to find a unique one that we haven't already added. I think this is nice to see, right? It gives us a sense of the underlying process. We may not actually. I'll let this run. It'll finish up, but I'm going to also move forward because there might be enough time for me to code a better combinations algorithm. I think there is. Okay. So this is based on itertools, and if you want to know more about itertools, you can just Google Python itertools, and itertools is in the docs. We've got all that stuff here, and there are a number of things in here. So we've got combinatoric iterators, we've got permutations and combinations, and the algorithm I'm going to show here is essentially the same algorithm that is in this library, and it's going to operate a little bit. It's going to not operate in the reductive approach that I just wrote. So let's see, did that finish up? Oh, that finished up. Yep, 20,349, and it probably slowed down quite a bit at the end. Okay, so we'll call this more optimal combinations, and this is the itertools algorithm. Okay, I'm going to use a keyword in here called yield. Okay, what yield is going to do is it's going to essentially take something in my function and throw it into a return as I go. So instead of collecting into a list, I'm sort of collecting into what we call a generator object, and that generator will allow me to pull things out after I run the function. So yield is a better approach, arguably, to a lot of things, especially if you're returning a list or some other collection. Yield tends to be a little bit better. But that said, you don't need to know about yield specifically for by the beginning of the DSI. It's something that you'll work with in the DSI, and you'll see it there. So I'll call this comms algorithm from itertools. And remember, we're passing in a list, and we're passing in a value of k. The list is going to be of length n. K is going to just be, how many items out of that list we care to put into a combination. So the first thing I'm actually going to do is I'm going to freeze that list, which may sound weird. There's a reason for doing that that I won't get into too much here. So I'm going to freeze the list, and I'm actually going to convert it into a tuple. That's how I'm freezing it. And I'm going to reference the length of that list as well. Okay, so here's my combinations collector, and I'm just going to put in a little bit of fault control, and this is the kind of thing that exists in functions a lot. If k is greater than n, well, let's just return. Let's return none. We should probably error in this case. We haven't covered error handling. Clark will cover error handling in one of the last classes for this course. But for now, let's just return maybe k cannot, how about this? K cannot be greater than n. Okay. So it's sort of like it's like an error, but it's not a true error. Okay. So I'm going to essentially make a collection of indices from our list. I'll just make list of range k. So this is a little bit like what we were doing to keep track before in our permutations approach, although here it's a little different. And the first thing I'm going to do is I'm going to yield that frozen list. Every element of that frozen list for the indices that we care about. So what does that mean? Well, this list is going to be range k. It's a pointer, or sorry, it's a record-keeping device for all the positions that we care about. This is k items out of n items, right? And so I'm getting all of these positions, right? So this will be 0, 1, 2, 3 up to k. I'm getting those positions out of that frozen list, and I'm yielding it as a tuple. So this is what I'm yielding is smaller, right? It's smaller than 21 or however many combinations we're trying to build. Or sorry, whatever our value of n is. It's smaller than that. It's going to be length 5, if we think about it that way. So while true, now this may be irksome because you're like, that will never end. We'll find a way to make it end, okay? While true, for I in, and I'm going to reverse this range of k. So what does that mean? 5, 4, 3, 2, 1. Or sorry, 4, 3, 2, 1, 0. If indices sub I is not equal to I plus n minus k. This is a little bit of math magic, but it's how do I say this? It's part of this process that we're performing. So this is kind of skipping over a bunch of things, if you think about it that way, right? We're not doing anything, we're not yielding anything, we're not collecting anything out of that for loop. We're skipping over potential potential arrangements that can lead to new combinations. Okay. And there's an exit condition. So we are going to, consider the I that is in focus, wherever this ends up, right? Wherever I ends up, we're going to utilize that, okay? And then I'm going to have this other value, j, in range, and we'll consider I plus 1 up to k. And we're going to, let's see, this 1 plus 1. We're going to take, we're going to increase this value, this index value, in our record keeper. And then once we complete these 2 for loops, we can yield a value. So this is very much like that initial yield that you saw. And what we're doing, in some sense, is we're rearranging what is in these, what is in this indices list. And through that rearrangement, we are collecting into a generator, or we could imagine collecting into a list. We're collecting the different combinations and neglecting the combinations that we've already collected. Okay, so let's call this on something. Let's call this on let's do the same value we have up here. So if we consider yeah, let's do that. I'm going to make this a list just in case. And let's look at every 5-person team from our 11 nums and see if this errors out. Okay, so team combinations gets that. So for com in team comms, let's print that combination and find out if that works. Okay, nice. Now these are all in tuple form, but that's fine, right? When we're yielding things out, we tend to put them in some sort of well, it's nice to have it as a tuple, and it's just frozen in this position anyway. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 1, 2, 3, 4, 7, 1, 2, 3, 4, 8, 1, 2, 3, 4, 9. There's kind of an intuitive pattern there, right? we're fixing these first 4, and we're solving 5, 6, 7, 8, 9, 10, 11. And then we're saying 1, 2, 3, 5, right? And we're neglecting 4 at that point, and we're saying 1, 2, 3, 5, 6, and we're going up to 11. And notice with each of these, there are sort of less and less, right? So there's, in this position that's 1 from the right, we've got 1, 2, 3, 4, 5. Then, so there are 5 6s, then 4 7s, then 3 8s, then 2 9s, then 1 10, right? Eerily similar to how we think about factorial. We can see these patterns. And it's important to start, kind of recognizing this idea of patterns, right? Like, if we give you something and we're like, hey, what pattern do you see here? What emerges from this? That kind of pattern recognition is really important. It's important when you're scanning through data. It's important in understanding sort of fundamentally how an algorithm works. Now, I don't expect you to understand exactly how heaps works or how this itertools combinations algorithm works. You don't need to know how to do that right now. But if you want to know how to do that, it's going to take looking at the output of this, right? If you want to understand it, it's going to take looking at this kind of output and being like, well, what's happening here? Can you do this by hand? Can you figure out how to do this by hand? Because that, if you can, then you can code something that does this. And whatever you code might look different from what I wrote, but that's okay. If you follow the same procedure that you're actually doing in the real world, then that is going to be the same algorithm, right? The algorithm transcends the language in that sense. So, yeah, we can continue to follow this down. There's going to be a lot less 4s in this third position than there were 3s in that third position. And then a lot less 5s, a lot less 6s, a lot less 7s. And again, we see this pattern, 1, 2, 3, 4, 5, 6 7s, and then 3 8s, and then 1 9, right? So as we move to the left, it's more dramatic how these numbers reduce, or how these instances of, say, the occurrence of 5 reduces. I think that might be kind of fascinating, like 1, 2, 3, 4, 5, 6 7s, 3 8s. Kind of cool. Okay. That's class for today. Hopefully that didn't fry your brains too much. We're not going to, how do I say this? You need to know permutations and combinations in terms of being able to code them, code the basic mathematical operations. And you need to be able to recognize a permutations problem. You need to be able to recognize a combinations problem and be able to solve it, using a function that you coded. That's important. Do you need to be able to write heaps? No, you don't. Do you need to be able to write, combinations, a combinations function? Do you even need to be able to write these reductive algorithms that I performed? Probably not. We're probably not going to say, okay, well, write a function that gives me all the combinations of, of this specific list of items. We're probably not going to ask you to do that for the technical interview. But that's a good thing to know how to do, because it is a sort of foundational way of thinking algorithmically. And so I definitely encourage you to go back through this code and pick it apart. Go through the slides, try to understand what's happening in those. Cool.